Hi everyone, welcome to this week's Spatial Spotlights with me, Helen from Carto. These are a series of mini webinars that we put on every couple of weeks, which go through a spatial use case or piece of analysis or data deep dive. They normally last about 10-15 minutes. As today is Valentine's Day, we're going to be doing a Valentine's Day special exploring dating patterns across New York City. So I'm just going to share my screen, and hopefully you can see that and my face doesn't disappear. So we're going to be exploring this really awesome data set that we have in Carto today called proximity data from our data partners, Spatial AI. So this data set is basically a geosegmentation data set. If you're not sure what geosegmentation is, it's basically a way of going deeper than sort of classic demographic indicators like population density or age or things like that, and looking into people's actual behaviors and characteristics. So this particular data set uses people's opinions and the things they talk about and express interest in on social media platforms. So things like Twitter, Instagram, Meetup, Eventful. And what it does is it has 72 different user segments and gives areas a score of 100 depending on how much they fulfill the characteristics of those segments. So for instance, today we are interested in one segment in particular called dating life. I'm just going to zoom in a bit so you can see this text a bit better. So this is described as, with dating comes highs, lows, and lots of questions. You can find the segment talking about dating advice, breakups, and how to express their feelings. So for instance, if an area scores 100, then people in that area are talking about dating all the time. It's all they talk about. They are going speed dating, they're asking their friends for advice, they're on Tinder all the time. They're basically really, really interested in dating. If an area scores 0, then they're not interested in dating. They never talk about it. So let's take a look at what this data looks like. So here's a map I've created earlier. Let's just zoom in to Central Park so we can use that as an example. So you can see this region has scored 84.97, which is a really, really high score. It's in the top 20%. So this means that people spending time here are talking about dating an awful lot. Whereas if we go over to, I'm sorry, I don't know what this region's called, but we can see this area has a score of 7.72, which means people are barely talking about dating at all. It's important to note that this data set is actually looking at people spending time in an area. So it's not residents. So it's not that there are residents of Central Park who are talking about dating a lot. It's the people who are spending time there, walking around there, working there. It will consist of residents as well, but it's basically where you are when you express that opinion. So it's really, really interesting, this data. You can see we've got very high values here around Central Park, some high values down here around Midtown as well. But actually, I think it's quite difficult to draw conclusions from this data set, like visually. And the reason for that is that we are looking, census block data, which is the source for this data, it's based on an uneven grid. Cells are basically sized by population density, which is why Central Park is very massive, because not many people live there. But you can see we have this huge zone for Central Park right here, and then this absolutely tiny, basically block right next to it. So this makes it really difficult to draw conclusions from this data because the zones are all different sizes, and for the human eye it's just really tricky. The other thing that's difficult about this is census blocks and other geographies like it, whether it's census zones, if you live in the UK like I do, we use output areas. These are uneven geographies, and this means they have loads and loads of vertexes basically. So let's use this zone down here as an example. You can see that this zone has probably about 100 different vertexes. So here's one. The way that geographical data is typically understood by platforms like Carto is through a geometry column, which is basically a long description of every single vertex that is in a shape. So it's the latitude and longitude of every vertex. So that means that this data is really, really large. It's really heavy to store, and that means it's really difficult. It's really slow to render. So as I start to zoom out here, you can see that we started to drop some features. So for example, if you can see where my cursor is, we've dropped that feature. There's some white spaces up here as well. And also the features that we've retained have become simplified. They've become a bit more jagged as we zoom out. So this means that as we start to analyze data at scale like this, if we wanted to look at all of New York City rather than just a small local area, it becomes even more difficult to make those visual conclusions from the data because we've lost some of it and because it's become much more jagged. So a really great way around this is to convert the data into a regular grid. And that's what we're going to do now. So I'm just going to head into Carto workflows. Oops, not that one. That's a spoiler. Don't look at that one. So if you haven't used Carto workflows, and by the way, if you're not a Carto user, you can head to carto.com and sign up for a free 2-week trial and try out all the things that I'm showing you today. But Carto workflows in particular is a low-code tool for developing these long, complex analytical pipelines, but in a low-code way that is very intuitive, very easy, very shareable. So that's what workflows is, and we're going to be using that today. So what you can see here is we've got just our geospatial segment data at the moment. So I'm just going to click on this, and this is we can just have a preview of it. So this is just our input geospatial segment data set. And I've just run a couple of filters on this just to narrow down to the data that we're interested in. So first of all, I've just filtered this just to a specific date that I'm interested in. And secondly, I filtered it to the comparison level. So what you're getting when you have that score of 100 that I talked about is where you have a comparison level of national, for instance, and if a zone scores 100, you know that area is top of all of the areas in the country because it's a relative score. Whereas here we're looking at the DMA level. So we know that if an area scores 100, it's top of that whole metropolitan area. So it's a relative score, essentially, is what I'm saying. And different comparison levels will be relevant to different use cases and analysis. In this case, we're really interested in the metropolitan area of New York. So that's what we're looking at here. So we have our geospatial segment data ready. So the next thing we need to do is create our regular grid. So to do that, first of all, we need to specify what the area is that we want to create a grid for. So I'm just going to head into sources, and you can see on sources, let's just close this so you can see a little better. On sources, you can either access data from your connections, so your cloud data warehouses, or the data observatory where you have subscribed to data from. So I'm just going to head into Carto subscriptions, and I want United States counties because we want to use counties as the basis for building our study area. I'm just going to head into this sneaky document and grab some code out of here. So because we want to do something a little bit fiddly with this filter, I'm going to use a custom SQL select to run a filter. So let's just wait for that county dataset to load. Actually I can talk through the code while that's happening. So what this code is essentially doing, it's really, really simple, is it's saying I want to select these 5 counties, which are the 5 New York City boroughs. And then what I'm just going to do is run a union ag on them. That will basically dissolve the boundaries between them. So it will turn them from 5 discrete features into one feature. And you can see we're using this callback here, the A callback, to call from here. So we don't have to always be writing out all of the qualified names. So let's just run that. Shouldn't take too long. So something to note about workflows is you can actually run this step by step, or you can run it all in one go once you've compiled the whole workflows. It's up to you. Anything that you run step by step won't be rerun every time you hit run unless you change anything. So you don't have to worry about every single component being reprocessed. So we can now preview that. So these sections along the bottom here are our previews. So we can have a look at the data preview and we can have a look at the map preview. So let's zoom in here. So great, we have our study area. Something to note while I'm here is also as you run this analysis, in the background, this SQL is being compiled. So if you want to take any of this and take it into your Cloud Data Warehouse console or anything like that, you can copy and paste this SQL, which is super handy. So we have our study area, but something I also want to do is run a buffer around this and just extend this study area out by, I'm going to say 10,000 meters, 10 kilometers. Because essentially when you're looking at spatial patterns, you want to be really careful about edge effects. So if I'm interested in looking at the spatial patterns within New York City, I want to actually look a little bit further than New York City because we don't want to assume that nothing is happening beyond the boundary, particularly if you're doing something like hotspot analysis, which we're going to be doing a little bit later. You want to make sure you're not just thinking that nothing happens beyond this arbitrary line. So that's run. We can take a look at the map preview. And now we have this kind of slightly more bulbous study area. So we're ready to go and convert this into a grid. So we're going to be converting this into a H3 grid using the H3 polyfill component. H3 grids are something called a spatial index, which are basically multi-resolution grids that cover the entire world. They have a bit of a superpower, which I'll show you in a second. But one of their really interesting features is they're hierarchical, so you can choose what resolution they are. So I've just changed this from 8 to 9, which is, I think, about 200 meters across for one H3 cell. But you can go all the way from 1, I think, to 22. And those cells all have relationships between them, so it's really easy to move between the different resolutions. You're not sort of stuck at this resolution. So let's go ahead and run that, and I can show you once that's done what the H3 superpower is, if you're not already familiar. So first of all, let's just take a look at the grid we've created. So we have our hexagonal grid covering our study area. Hopefully, if this video is large enough for you, you can see that as I zoom in, we're getting more and more detail. So if you think back to earlier when I was saying, as you zoom out and make more scalable, try and get more scalable insights from your data, it becomes harder and harder to do that with those census blocks or with geographies like that in general. With spatial indexes, they basically aggregate at different zoom levels, so you're always sure you're getting sort of appropriate levels of data for the zoom level you're looking at. And it also means you're never going to be in danger of dropping data or data simplifying. It always works really well at scale. But the H3 superpower is this. It doesn't look much like a superpower, but I promise it is. So if you think back earlier to when I was describing how geometries work by having latitude and longitude pairs for each corner of a shape, which is really, really heavy, H3s are geolocated in a different way, or spatial indexes in general. H3 is just one type of spatial index, but they're geolocated in a different way with basically this. So this very short reference string basically tells programs like Carto where to put that H3 cell and how big it should be. And that's all it needs. This can also be used to, like I mentioned earlier, move up and down between different resolutions. It can be used to look at neighbor relationships. There's so much information that's contained just within this string, but it's tiny. And that means this data is really small to store and really, really quick to analyze, which is fantastic. So the next step, very straightforward, is we just want to enrich that grid with our dating life index. So we just need to, in variables here, go down and find dating life. If I can, here we go. Dating life, we want the average, and we're just going to run that. So what this is doing is basically taking all of the census blocks, all 217,000 of them, and all 27,000 H3 polyfills. And you can see that only took 15 seconds. I didn't even finish describing the process before it finished. So that's a massive amount of data, and it's basically doing a cookie cutter on them and working out what percentage of the census block overlaps with what percentage of the H3 cell, and assigning the dating life score based on that sort of spatial weight. So you can see here, if I just open the data preview, we have our H3 cells and we have our dating life score that has been proportionally assigned to each cell. Don't be afraid of the nulls, because these are values that are in the sea. For some reason, it's always the sort of mid-ocean cells that come up first, because if we take a look in the column stats preview, we can see that we do have lots of data in here. So these are just in the sea, and I can show you that. In fact, I can show you that right now. So from here, if I go into the map preview, I can just hit create map, and this will create a really quick map in Carto Builder without me having to do pretty much anything. So here is our data that we've just created. I can quickly style this up so we can see the data that we're looking at. Dating life average. Let's change this to quantile. Great. So with H3 cells, like I mentioned earlier, as you zoom in and out, they sort of aggregate and disaggregate, and you get different zoom levels, different sizes as you zoom in and out. But you can control that yourself. So for example, up here in the resolution, you can say, oh no, I just want to see, for some reason, a very coarse representation of this data, or you can zoom in, you can turn it right up the other way and say, I want it as detailed as possible, which is this. So if we zoom in here, we can see that we've got some very high values around. Let me just change the base map so it's a little easier to see. Some really coarse values around Midtown New York, around Central Park. Lots of people interested in dating around here and up here as well, in this sort of region as well. Sorry, my geography of this area isn't very good. So if I was working at a dating app company, I might think, hey, these are really good areas for me to do some advertising, maybe some like targeted marketing, maybe try, if I don't have much market saturation or penetration in certain areas, I could try and have some offers in those areas to try and pick up more of these customers. But what is still a little bit difficult about this is it's still quite qualitative insights. So it's still me looking at this map and being, oh, there's quite a lot happening. There's quite a lot of interest around here. There's quite a lot of interest around here. But it's not very concrete. So the final thing I'm going to show you today is hotspot analysis, which I mentioned briefly earlier. So let's just close this map and go back into a workflow I created earlier. So this is hopefully something that's familiar to you because this is the workflow that we just created where we're creating a H3 grid and we're enriching it with geospatial segment data. The next step that I have moved on to is creating hotspot analysis. So I'm doing that with this component called getIsOrd, which basically takes a grid like H3 and works out where you have statistically significant clusters of your data. So where there are really high values of people really interested in dating life and they're all clustered in one area. So it means that you can make really quantitative, really certain conclusions. So I've done that with the dating life component, but I've also taken a look, dating life segment, but I've also looked at a couple of other segments that are in the spatial AI data. So I've looked at hopefully you can see this, I might zoom in a little so it's a bit easier, the happily ever after segment, which is basically people who, rather than necessarily talking about dating and going on dates and things like that, they're sort of the more late stage daters. They're the people who are thinking about marriage, they're thinking about kids, they're thinking about moving in together. So this is kind of where you start to think about how different types of dating apps might want to target different types of people, or actually not even dating apps. Like this could be great for people working in the wedding industry. We know one of the biggest industries in the world. So we're taking a look at that as well. And then the final segment we're looking at is LGBTQ plus culture. So where there are people talking about all sorts of cultural aspects related to LGBTQ plus activities. And then these couple of extra segments here are just a bit of data cleanup. So I've just renamed the columns so we don't just have 3 columns called GI because that would be very confusing for my brain. And then I've just joined the outputs of this data back to the original H3 grid. So what we have here, let's just quickly look at this data before I show you the map, is we have H3 cells, we have all of our indexes, all of our segments, the scores against each of those segments. And then for each of our segments, so dating life, LGBTQ+, and happily ever after, we have a p-value and a GI score. So the p-value is we are only interested in really low values here. So I'm filtered this data to only where there are values of less than 0.101. So we're basically looking at where we have a really high confidence level that these are statistically significant clusters. And then we have the GI dating life score, which is basically the GI score, that is the strength of the cluster. So we're only interested in higher positive values for this. So now we can see the results because I've already pre-run all of this because I didn't want you to watch me trying to connect all of these workflow components together. So first of all, we have our dating life hotspots. So you can see these reddy orangey areas where we have hotspots of the dating life segment. So this is exactly the data that we were looking at earlier, but it's converted into hotspots. And you can see how much easier it is to draw conclusions from this data rather than trying to work out where there's darker areas or lighter areas. This immediately says, here's a hotspot, here's a hotspot. So that's what we're looking at with dating life. Next, let's take a look at LGBTQ+. So you can see much more clusters across the city, really. There's much more more distribution across the city. We can see Manhattan is a real hotspot all along the length of Manhattan. And if you remember earlier when I was talking about edge effects, that's what we're getting here, but that's okay here because this is the river. So there is a genuine edge effect here. But if we were seeing these edge effects along here, which we're not because we can see there's overlap here, that would be a problem because there's not a real physical edge here. There's loads of people living here. So we want to think about them as well. So yeah, we have our hotspots all along Manhattan, a lot in Brooklyn as well. So that's the LGBTQ plus culture segment. And then finally, we have happily ever after. And I think this one is really interesting, particularly when you compare it to dating life, because this is kind of what I would expect from any city. So I live in London, and this is definitely what you'd experience in London, where you have younger, maybe more single people living more centrally, so Manhattan, Brooklyn, these sorts of areas. As you get slightly older, you're settling down, you want a bit more space, you're thinking about that house, you're thinking about marriage, then you start to, as we can see, migrate to these more outer city areas, these more suburban areas, I assume. So I think it's really interesting to look at those in comparison. And then finally, I'm going to turn all three on and it's going to look a mess. But something I have here on the right, be good if I knew the difference, is I've got these widgets which basically show the average GI score across all these regions for our three different scores. So we can see that we really have the strongest clustering in our LGBTQ plus segment, followed by happily ever after, and then followed by dating life, which kind of makes sense because I feel like dating life is kind of the broadest of the three segments. The other two are a bit more defined, I suppose, and it makes sense then that they would be a bit more spatially defined. So that's pretty much it from me for that. I think I've lost my camera. Very sorry about that. Don't know how that happened. Normally, who knows? But thank you so much for coming along and listening. I hope you enjoyed the session. We have another one again in 2 weeks with my colleague Matt, who will be talking all about the workflows gallery, which is basically you saw me building a workflow and putting one together today. We also have a gallery of templates, which you can basically use as sort of blueprints for starting your own analysis, but he'll tell you more about that in 2 weeks. So if you're interested in learning more about low-code analysis, please do come along to that. Otherwise, thank you for coming. Have a great rest of your Valentine's Day and catch you another one of these soon. Thank you.